Right. So as we know, AI has taken large steps in recent years, and it's come to the point where a lot of our bottlenecks are coming not just from the generation of the models, but also from their evaluation. And so models can think that, or we can think that these models are safe or reliable, but in the end, we can't prove it without proper evaluation metrics. And so this talk is about characterizing and mitigating the misalignment between the evaluation of generative models and their intended use cases. And this is an evaluated talk for the RGMV workshop, and I am from the Active Perception Group at Arizona State University. So this image here really embodies the idea of misalignment in evaluation. So it's originally intended for sort of pointing out the flaws in the education system. So the idea is that you're going to have all the animals climb a tree as their final exam. And to say that a fish could climb a tree is not really that accurate. But at the end of the day, fish are very successful in their own environment by simply swimming, right, rather than climbing. And so just because a model can't climb the tree doesn't mean that it can't be successful in the actual use case. So first, I will give an overview of the two papers that I'll be discussing today. So I will be discussing a paper on evaluation of captions. And so to do that, we look at quantifying semantic understanding and linguistic understanding, which is also relevant to both vision and language spaces, since we still mostly understand vision distribution drifts and whatnot in the form of semantic representations. Like in the earlier presentation, we saw that she would discuss semantic versus stylistic changes in images, but those don't really make sense unless you have a label for the salient object. So all of these are sort of multimodally relevant, right? And so looking at how this typical paradigm works, we have a vision space, which could be images or videos, and this is sparse, meaning only a small set of the combinations of pixels are actually part of the image manifold or realistic images. And then in order to actually practically generate either vision or language, text or images, you have to map these signals to a joint multimodal space, which is dense and task defined. And so you've gone from something in the wild to something that you've defined yourself based on your pre-training task. And then, like the vision space, the language space is also sparse and defined by the number of combinations that you can have of different words or tokens. And so the first work will be dealing with captions, and the second work, image segmentation. So both of these works rely on typicality. And so we say here, what I'll be talking about here is how typicality can mitigate this misalignment between between your evaluation and your intended use cases. So the reason why this would work is because you're sort of getting a semantic signal from your use case that you will characterize and use for that evaluation. And so you want to assume that there is this underlying random variable process generating that semantic signal. And we estimate the distribution of this process or create a reasonable surrogate. And then you can use this estimation to get the variation between some input and the surrogate or estimated distribution. And we'd like to do this specifically for evaluation in a rule-based manner typically, because that helps with overfitting, right? We want our evaluation to work across multiple domains. And so our first work, the from Smurf, published at ACL 2021. In this work, we asked the question, what are captioning models lacking? So we see that humans often include very detailed text or words in their captions, like Dutch Hound or Indiana Jones. And when machines generate captions, they tend to generate the most typical instantiation of the sentence, which may not uniquely describe the image. And here we see a typical output from a machine model might be a bunch of bananas sitting on a table. So existing metrics at the time, and likely still, only really looked at the semantics, but never really are able to capture these additional details of Dutch Hound and Indiana Jones and like reward those. So this is especially significant because if you're not including additional style in the image, you may actually be able to get a better semantic score because you're not taking the risk of uniquely describing the image. And so we see that there's a lot of images actually have surpassed human annotations in terms of their semantic scores, a lot of captioners, but they still are severely lacking in terms of their stylistic qualities. And so in order to overcome this gap, it's necessary to actually consider stylistic criteria. So here we have, in our paper, we have a semantic score and a style score, which I'll go into the details of now. So the semantic score first removes stop words and stems words in order to create a concept distribution based on document frequency, where captions are the documents, and compares it against the machine generated text in order to create a adjusted F1 score. And we refer to this as sparks. So this is how we embody the semantic process. And then and we see here that this means of semantic representation for evaluation is actually state of the art. And it differs largely from previous works because we look only at unigrams rather than at sequences. And by looking at smaller components, you can get more correct solutions and not limit yourself in your evaluation. And in fact, it's so good that it actually surpasses the voting-based human comparisons. And we're actually comparing here against Likert scores 1 to 5. So voting is inferior in this case to our metric. And so then in order to fully grasp the full quality of captions, we also have to look at fluency. And so when you're looking at fluency or style, it's useful to consider it in terms of our idea of typicality, where you have the full set of combinations that can occur, but then there's actually only a very small typical set that of captions, or maybe in image generative models of relevant realistic images that will occur. And when you're making a metric of whether or not these occur on the manifold or are stylistically relevant, you can consider the distance from the expected value in the feature space of the features after you embed all the members of the typical set. And then you look at the distance from this embedding. And as your distance increases, your style and diction increase. But as it decreases, the coherence and grammar improves. So specifically for our work, we create a typicality measure using the self-attention mechanisms of Bert and Roberta. And we consider information flow, which is the mutual information of the attention head. So you could think of the tokens that are attending to one another as a joint distribution, and then take the mutual information of that joint distribution, and then take the max across the heads and the median across the layers, and then subtract that from 1 to get the MIMA score. And to validate the effectiveness of this, we look at an experiment where we degrade a sentence. So the original sentence is proof is a matter of figure. And we substitute words that are random into the sentence. And we see that our score based on Roberta is able to capture the degradation of the sentence in a monotonic manner. So you can, and so we want to see practically how could this be used. So in as an evaluation case, we look at grammatical understanding, and we see that our metric is able to judge whether grammatic corrections made to a sentence are the same as the judgments that the humans made, and which grammatical corrections were more correct. And we achieved state-of-the-art results on the Connell 2014 dataset. Sorry, I think it went back. Oh, yeah. So then we fuse the metrics, and I'll not go into details here, but they're based on outlier rewards and penalties, and standardization of the metrics. And we are able to achieve state-of-the-art results on caption evaluation benchmarks. So next, I'd like to talk about the work that I presented here for this year at WACV. So it's towards addressing the misalignment of object proposal evaluation for vision language tasks via semantic grounding. So the idea here is we're using typicality to identify examples that are the most relevant. And specifically the task that we're testing this mechanism on is object detection evaluation. So a typical object detector generation looks like this. So you have an image and then region proposals from the image and labels for each of those regions. And then you can take those regions and you can look at the features of the latent state features from the model and get region proposal features as well. And these are commonly fed into downstream tasks. And I've also seen these within this own conference, seen regions like this used in image quality evaluation. So the question here is, are all the evaluation examples equally important when you're creating a detector like this that's going to be used for downstream tasks like image quality evaluation and image captioning? And the answer is no. So in our initial experiment, we see that only 50% of the ground truth annotations are actually contributing to downstream performance. And so we see that even if you only included half of the object proposals, you'd still get the same performance, and you'd still generate the same caption, in fact, in this particular qualitative example. So now, so this is a formalization of this issue that we're talking about here. So we see here that we use mutual information to measure the alignment between between a typical set of the object annotations and the and also the full set of annotations and the downstream task. And we consider that the alignment will be nearly the same for the critical annotations. And so if this is the case, which we find to be the case in caption evaluation, then your ranking of the detectors will likely be incorrect depending on the severity of this misalignment, which is caused by the size of the typical set. So if you have a very small typical set and a lot of these superfluous annotations, your ranking will be enormously skewed by the superfluous annotations. And so this is a summary of what I'm talking about. So what happens is your evaluation in your upstream task is actually making a poor selection of models or methods that would be helpful for the downstream task, which in this paper we explore the use case of captioning. And so this misalignment gets worse with a smaller typical set, and it's also applicable to all object detection and potentially many other related tasks. So how do we say that one annotation is more important than another? So in order to do this, we look at captions for each of the images. So here we have 5 captions from Coco, and we take keywords from the captions, and we generate a score, and then we distribute that score to each of the objects in the image based on their area. And then using an inverse distance matrix and graph signal processing techniques, specifically a heat kernel to disperse the importance, we can get final importance scores for each of the objects in the image. Now, let's look at whether these importance scores are actually useful and actually effective in their ranking of the objects. So we see that we have perfect rank correlation for downstream caption evaluation metrics, those being Meteor, CIDR, SPICE, and SMURF. So we are able to achieve perfect rank correlation with these downstream metrics when we use the selected ground truth annotations using our weighting, our scoring. So in order to split up these groups of captions for use by the captioner in the downstream task, we look at the deciles, or the 0 to 10th percentile, 10th through 20th percentile, and so on, in 90th through 100th percentile. And then each of these points represents one of those percentiles. And we see that this is what I mean by the perfect alignment between the upstream evaluation and the downstream task. Now let's look at whether these scores are well aligned with what humans think to be important in the image. So in this case, we have detector annotations from one detector and detector annotations from another detector, and one is on the left and one is on the right. And a human makes a choice between the two detector annotations, and the model does. And so we see that many standard metrics have no correlation with the human choice, whereas MAP50, which is the common metric used for evaluating detectors specifically for vision language tasks, has 70% alignment. And then we propose an additional recall measure, which have 75% alignment. Then when we also incorporate our thresholding criteria, we achieve up to 85% alignment with human judgment in selecting which portions of the image are the most salient and useful for and relevant to the scene. Now let's take a look at whether our approach can actually generalize to different types of annotation techniques. So visual genome and COCO have shared images. So we look at the visual genome annotations and the COCO annotations, and we see if when we increase our threshold for selecting images, whether the overlap between these two data sets increases. And we find that, yes, the IOU is increasing significantly as you select fewer and fewer annotations. And here's a visual example. And we see that we go from having a background information like lights to having only foreground information like face, shirt, tie, and hair, and the man. And so that is what is contributing to this increased IOU between the two data sets. Then finally, we propose a adjusted detector evaluation benchmark based on our scores. And we modify an existing scene graph generation benchmark, and we threshold the visual genome annotations based on our prior experiment. So we have two threshold values of 0.075 and 0.3. And we modified the data sets, and now we have our precision recall and F1 scores for these two different threshold values. And we can see that we have misalignments can occur between our new measure and the existing measure of just using map 50. And so we are providing a much more nuanced view than is currently available, and can help you debug whether your detector is useful for your intended use case. So in conclusion, we use typicality to improve the alignment of upstream evaluation and downstream use cases. And our typicality measure can be used to create both references and reference-based metrics. The example of references was our style-based metric from the Smurf paper. And typicality evaluation paradigms offer more explainability and better use case targeting in your evaluations. And future work can focus on applying typicality to other modalities, including vision, radar, and the joint spaces between these modalities. And that's all for my talk. You can see my papers on my website if you just www.myname.com, or just Google my name, Joshua Feinglass, and you can find my website. Thank you.